Okay, I'm going to regard this chapter as Noether's theorem. Eventually we'll be doing a theorem that's called Noether's theorem, and that will be the ultimate aspect of the structure or the aspect of conservation laws in general. Let's just recall some concepts that we have looked at in the previous chapters. You may recall that our one parameter Lie group of transformations had a certain representation, a one parameter Lie group of transformation via a parameter G looked like the following. So if we took the parameter G star, that is the map that acts on the variables x, y, the transformation we called x bar, y bar. When this was extended to the jet space, in which case we assume that y is a function of x, then the G star acted on x, y, y dash, and all subsequent derivatives too. So you could get y double dash further on. And that transformed as x bar dashed, etc. We also showed two things. One is that each one parameter Lie group of transformations can be represented in vector field form, so that in the first case the vector field would be G given by, or we may have, let me use the variables, the notation we had earlier on. So the vector field representation would be xi d by dx plus eta d by dy. In the jet field representation, the corresponding vector field in the first order case we called x1, and that was x itself, which is xi d by dx plus eta d by dy plus what I called the prolongation eta 1 d by dy dashed. I need to write this a bit better. So if we write it slightly better, this will be eta 1, and this is partial d by dy dashed. That was the operator. That's a plus sign as before. And this could be prolonged to second derivatives, etc. But in the prolongation, of course, the eta 1 depended on xi and eta. So that, for example, eta 1 was equal to the total derivative of eta with respect to x, and that's total derivative, plus y dashed, the total derivative of eta with respect to, this should be xi with respect to x. This is xi with respect to x. And there was one other aspect, and this was quite important, in that we showed that if we expanded x bar, y bar, and similarly y bar dashed up to first order in the parameter G, then the x bar, y bar dashed had a formation or a structure that included the xi's, etas, etc. So let's just recall that too. Okay, so let's go back to this. So recall another aspect, and that the x bar could be written as up to first order prolongation as x plus, and this was important, it was the parameter multiplied by xi, and then of course you got the higher order in the parameters. Y bar was y plus g eta, and if we continued in this way, y bar dash will be y dashed plus the parameter g and then eta 1, etc. So the coefficient of the g, the first order in the parameter, g to the power 1, gave us in fact the coefficients in the vector field. So that you notice then that xi here correspond to the xi there, the eta there corresponds to the eta there, and eta 1 corresponds to the eta 1 there. And that was the coefficient of g if our parameter in the one parameter Lie group of transformation was g. I would eventually give a set of notes. Let me remind you that the parameter used may not be g, it could be alpha, it could be epsilon, it's just a matter of notation. Okay, the next thing to recall is we said that a function is left invariant under a transformation, a one parameter Lie group of transformation, if the function remains the same. So the function f of xy is invariant, right, under a one parameter Lie group of transformation, under, let's say, because this particular one parameter Lie group of transformation, if, and this was a definition, that if f of x bar y bar equals f of xy. Please look at the details of this in the previous chapters. And of course, we extend this to derivatives also. So if we extended this, it's x bar y bar dashed equals that function on x, y, and y dashed, like so. This was the definition. And very importantly, that if a function f is invariant under a one parameter Lie group of transformation, and this was a theorem, that then the vector field on that function is equal to 0. Or if the function included derivatives, a differential function, then the vector field prolonged on that function is equal to 0. In the case of differential equations, if a differential equation is invariant under a one parameter Lie group of transformation, again look at the previous chapters, then this condition had to be satisfied and the differential equation itself had to be satisfied. So just recall that here it is just a function that is invariant under a one parameter Lie group of transformation. For a differential equation to be invariant, you needed the respective condition like that to be satisfied, and the differential equation itself needed to be included somehow. So again, all of that is contents of the previous or chapters previous to that too. Now what we're going to define is, under a one parameter Lie group of transformations, how would a integral be invariant? Now in the calculus of variation, what are we doing? We're looking at a function, or we're looking at functions that optimize an integral of this type if we're keeping it up to first order in derivatives. So this was the functional that defined the problem in the calculus of variations. We're looking for functions that leave this invariant. And we said, for our purposes, that the function that leaves this integral optimized is a function that would satisfy the differential equation, which we call the Euler-Lagrange differential equation, dl dy minus total derivative dl dy dashed equal to 0. This was the Euler-Lagrange equation. So now we're going to study the invariance of this integral. So we're only now starting with the notion of the invariance of this integral, but we're going to do a little more. Okay, so we're taking, so if a one parameter Lie group of transformation G star on xy leaves that integral invariant, then this has to be satisfied. And it's almost obvious why. So the function, or at least the functional, the integral, if we replace the x, y, and y dashed with x bar, y bar, and y bar dashed, this has to be equal to the same integral with the variables x, y, y dashed. So I should say, if this is satisfied, then the integral above, the functional, that's the integral that I have put in a block above, the functional, which functional? That functional. Then the functional that is invariant under this one parameter Lie group of transformation. The one parameter Lie group of transformations I've defined here. But what we're going to do is, when we study this equation, this invariance of this integral, we're going to add in an extra term, and we're going to say that it is not just invariance we're going to look at, but it's going to be invariance under a gauge term. So we say, right, the functional, that same functional above, the integral, the functional is invariant, right, under this one parameter Lie group of transformation. And here's the extra bit, up to gauge. And this gauge term really is a product of something in physics, but there are some nice mathematical consequences. Up to gauge, and I'm going to give the gauge a name, say up to a function xy, which is gauge, if we have this invariance property and a little more. And here it is. I'm going to do this in a slightly different color. So if the integral of x bar y bar dashed dx bar equals the integral of L of x y dashed as an integral with respect to x, plus g, which is your parameter in the one parameter Lie group of transformation, multiplied by this function of xy. And what we're going to study now, so this is in essence the invariance up to gauge of our of a functional, the integral that is used in the calculus of variations. So this is what we're going to start off with, and this is an invariance property, up to gauge. Invariance for the exactness means f is equal to 0. Right, so what happens as a result of this? Well, as a result of this, we get the following. I can write this term f as an integral so that I have every term in an integral form. So, sorry about that. I just need the correct color. Okay. Or, let's write this differently. The left hand side, L of x bar y bar dashed dx bar equals the integral L of x y dashed plus g, the integral of the derivative. So I haven't changed anything. So I have every term in terms of integral, and what I'm going to do now, I'm going to differentiate both sides with respect to x bar, knocking off the integral on the left hand side. So what I'm going to say is I'm going to differentiate the left hand side with respect to x bar, and I'm going to differentiate all of the right hand side with respect to x bar. Let's do that a bit nicely. So this is equal to, and this is the derivative with respect to x bar of all of the right hand side. On the left hand side, as a result, the integral disappears. So therefore, on the left hand side, what we end up with is L of x bar, y bar dashed, and on the right hand side we need to rewrite that derivative with respect to x bar in terms of x using the chain rule. So this differential operator d by dx bar can be written as, let's suppose it operates on some appropriate function, can be written as d by dx multiplied by dx bar. So we can do that. Okay? And so this derivative on the right hand side I'm going to replace with that, for obvious reasons, of course. So on the right hand side we get then that this is dx by dx bar d dx of all of the right hand side. And this time when we differentiate the right hand side with respect to x, we knock off the integrals. So I'm going to do two things. This term now I'm going to take to the left hand side, and on the right hand side we just do a differentiation. So we're doing two things here. So this becomes dx bar by dx multiplied by what we had on the left hand side, L of x bar y bar dashed equals, and then when we do the derivative of the right hand side, the integrals disappear. We end up with L of x y dashed plus the parameter g df by dx. That's after differentiating the right hand side. What I'm going to do next is to write out the x bar, y bar dash on the left hand side in an expanded Taylor form. So we get, therefore, up to first order in the parameter. Therefore, on the left hand side, we get the derivative of x bar with respect to x multiplied by, I'm going to expand the function L on the left hand side eventually. So first of all, x bar is up to first order derivative x plus g times xi. Y bar is y plus g times eta, and y bar dash is y dashed. That's y dashed plus the parameter eta 1. You scroll above, you'll see this. And the right hand side remains what it is from there. Now let's do some expansions. If you differentiate x bar with respect to x, that becomes, you differentiate x bar, you get 1 plus g times the derivative of xi with respect to x totally. That is this term here. If I expand that in terms of Taylor series, this is L of x, y, y dashed plus, up to first order expansion, we've got the parameter g, xi times the derivative of L with respect to x. So it is this g times xi, the derivative of L with respect to x. This is the first, this is using partial derivatives, plus g times eta, that is now this term here, g times eta, the partial derivative of L with respect to y, plus g times eta 1, the partial derivative of L with respect to y dashed, and that should close the curly bracket on the left hand side, equals the same right hand side, which is that right hand side. We're going to do some multiplications. That means the round bracket on the left hand side is going to be multiplied into the curly bracket on the right hand, on the left hand side, only up to first order in G. So if you multiply the 1 into the curly bracket, we end up with L of x, y, y dashed plus g xi dl dx plus g eta dl dy plus g eta 1 dl dy dashed. Then multiplying this term into the curly bracket, just up to first order in derivatives, we get g dxi dx times L. Let's write that down. So we get plus g total dxi dx times L of x, y, y dashed. And the right hand side is exactly what it was before, namely L of x, y, y dashed plus g df dx. Therefore, if we simplify this, on the left hand, well, the L from the left hand side cancels with the L on the right hand side, and then equating powers of g, we end up with, on the left hand side, xi dl dx plus eta dl dy plus eta 1 dl dy dashed plus L times total derivative of xi with respect to x. That's on the left hand side. On the right hand side we have df dx total. You notice that these three terms, in fact, if you look at closely, that is your operator x, your vector field x operating on L, but prolonged up to first order derivatives. So the left hand side, at least the part that I've indicated, which is that part there, is in fact your vector field x prolonged acting on L plus L dxi dx equals df dx. What this means is that a one parameter Lie group of transformations, x bar, y bar dashed, leaves the integral in calculus of variations invariant, unchanged, if this is satisfied. So these are equivalent statements. Etc. Highlighting. So this is the vector field version of the invariance of the integral in the calculus of variations. We'll take a Lagrangian of some equation, a known Lagrangian of a known equation, and find the vector fields that leave invariant that integral in the calculus of variations. In other words, we'll plug a Lagrangian into this equation and see what kind of vector fields we end up with. So next time we'll do an example of this type.